Hello, my name is Bauer Zhang. This is my submission for Lab 4, Magnetic Braking with Faraday. The purpose of this lab is to collect observational data of a bar magnet falling through an aluminum foil tube and model the interactions between the magnet and the aluminum foil surroundings using Faraday's law. Here is a brief preview of the results of the lab. The main physics principles used in this lab are Faraday's law, magnetic force on a wire, and Newton's second law. Faraday's law states that the magnetic flux through a ring is a dot product of the magnitude of the magnetic field and the area through which the magnetic field flows. The change of this flux is used to calculate voltage, and with this voltage, we can calculate current. Using current, we can move to the magnetic force on a wire. With the formula shown, we can calculate the magnitude of magnetic force on the magnet. Finally, with the position and velocity update formulas, we can accurately determine where the magnet is within the aluminum foil and for a given time, as well as calculate its velocities. The system, this assumes is a bar magnet. The surroundings is aluminum foil and the earth, and the initial conditions is that the magnet falls from rest. For the experimental data, here are the results. This is the time that it takes for the magnet to fall through the aluminum foil tube. With that out of the way, we can head to the code. Here we define the geometry of the aluminum foil. Here we define the properties of the magnet. Here we define a method to calculate the magnetic field of the bar magnet. Here we create another method to calculate the change in flux using the equation from earlier. Here we calculate the gravitational force on the magnet. Here we calculate the current in the ring. Here we calculate the magnetic force on the magnet and add it to the gravitational force to calculate net force. And here we use position and velocity update for the bar magnet. And this is the result. Interpreting the results. When the magnet is flipped around, the magnetic field and induced current are flipped, with everything else remaining the same. Comparing the results of the computation model to the real world model, the numbers are much different, but there are many explanations for this. Possible sources of error include negligence of air resistance, human error in time measurements, and errors in calculating mu naught in the previous lab. What if? What if the resistance of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? With the near zero resistance, the current would increase maximally to sustain the same voltage. With a larger current, the magnetic force would increase, resulting in the magnet falling much slower. What if the holes What if holes or slots were cut into the tube? How would this affect the ring currency model? The holes in this tube would disrupt the induced current and decrease it. This decrease in the induced current would decrease magnetic force and therefore increase the speed of the magnet as it falls. And that wraps it up for lab 4.